I'm gonna hang up this phone. And so, oh, there's the sandbox. Cool. Hey, everybody. That's great. I guess I'm a big head on the screen. So I'm going to use slides, but very minimally for this. I've I sort of have a philosophical uh, gripe with using PowerPoint slides heavily, and it's actually tied to my whole theory. And so we'll get into that a little bit. But it's the language itself. Language is this magical tool we've got that is uh, somehow constructed in such a way that we're able to generate arbitrary representations, thoughts, sensations, perceptions in other people's minds, and it's uh, a million, maybe it depends where you want to put the sort of evolutionary origins of language or where you want to date it, but it's a lot older than PowerPoint. Let's put it that way. And what I mean to say is that for most of almost all of human history, besides the very, very recent past, we've communicated almost primarily, almost exclusively through this kind of auditory channel. And to the extent that we've had to kind of communicate and convey information that may need some sort of visual aid, that would be a very restricted and small proportion of the time that we end up having to talk. So that's a long-winded way of saying that I'm going to try to keep slides to a minimum because I really want to kind of make this conversational. And I think there's something very powerful in just listening to somebody talk. And that's a little bit of and it's my own polemic against the heavy use of slides, which became sort of the standard in academic circles. Unless you absolutely need a slide, unless you're showing, for example, complicated data where visualizations are essential. I really think that people should try to avoid using slides and try to avoid using visuals because language is designed to operate in the auditory channel. In any case, so that being said, today we're going to talk about this very broad, I consider it a sort of a unified theory of cognition. I'm not going to cover the entire thing today because obviously that's a pretty tall order. And today I'm going to primarily be focusing on the implications of this theoretical framework that I've been developing for memory. And so the key core concept here is that memory itself is not what we have thought it is for certainly most of scientific history and probably for much of human history. I think that the advent of large language models and the computational framework underlying large language models has given us a radical new insight into the nature of memory and more broadly the nature of cognition. But today's emphasis is going to be a little bit more on memory. And that's in part that's because for the purposes of the kind of research that I'm doing and some of the extensions of this, some of the actual empirical and behavioral research that I'm pursuing right now, in fact, in some of a collaborative with some folks at FAU, that is a very strong emphasis. The theoretical framework that I've been developing is about language. It's about more broadly about cognition, but memory is a very important component of that. So with that being said, I am actually going to start off this little talk with a little bit of a memory test. So we're going to do a little demo here where I'm going to give you guys, what I'm going to do is I'm going to read you a sentence and I want you to try to repeat it back exactly as I said it. Okay? The good professor had come to the conclusion that the basic machinery that makes large language models run may also turn out to be the key to understanding how our minds work. Okay, think about that for a few. So, do you think you could repeat that sentence back verbatim? How about the sentence before it? So this is actually a little trick. Does anybody think that, now I'm not going to actually query you here because it's kind of awkward on Zoom, but does anybody think that they remember exactly what the words are? So just asking yourself, you can raise your hands if you do. You can raise your hands digitally or in the sandbox. The sentence that came before, the good professor had come to the conclusion that the basic machinery. So you may have memorized that one, and maybe you still remember it, or by now you might have no longer have access to the exact words. But there was a sentence that I said before that. And okay, you remember the qualia, but not the words somebody wrote. So these were the words. I'm going to read you a sentence, and I want you to try to repeat it back exactly as I said it. Okay? And I actually wrote that down. That's my little notes. That's my only notes for this talk. So in the parlance of cognitive psychology, in terms of how we operationally define memory in this context, we would say that you don't remember those words because you're not going to remember them tomorrow. You didn't remember them right now, 30, 40 seconds after I said them. And for all intents and purposes, we say, operationally, those words are gone. So somebody, as Dugan is saying, uh, I remember the meaning, but not the words, right? Now, there's a good chance you didn't even necessarily remember that I said a sentence. I was kind of blabbering on, as I want to do. And then somewhere in there, I threw in that sentence, and it was instructive. And the sentence was instructive, and I told you to do something. Now, when I got to the second sentence and you started listening to that, and hopefully you were trying to remember those words, the good professor, I come to the conclusion, and so on. The thing is, you were clearly guided by your uh, knowledge or of what I had said before. Meaning, even though you weren't able to actively retrieve that information, even though you weren't able to repeat those words, maybe you didn't even remember that I'd said the sentence, it's obvious from your behavior, and even as we're discussing now, it's obvious that you actually do have some memory of that information. So this little simple demonstration actually tears a big uh, gaping hole in what has been sort of an orthodoxy, as a kind of a standard notion of A, what memory is, and B, how we test it within the field of cognitive science, field of cognitive psychology. So this is one, I have to show you one image here because it's a very familiar one that people uh, often if you take cognitive psychology, if you take my class in cognitive psychology, you will see this. Let me see if I can share the screen here. Make sure I don't close the wrong thing. All right. Okay. So there's this very widely disseminated idea of these three kinds of memory. And let's see if I can show this. Oh, that looks terrible. A little bit off the screen, but so this is the modal of memory, or in this is an updated version called working memory. And this is a term you'll often encounter if you are hanging out with people who study memory in cognitive science circles, neuroscience, or psychology. And the basic idea is that we've got these different memory stores. There's a sensory store, which holds information very briefly for say 1 second, and then there's something called working or short-term memory, which holds information for 30 seconds or so. In the working memory model, you can manipulate that information. And then there's this long-term memory. And so long-term memory, in theory, if you can live forever, you can hold on to that information forever. And the foundational idea behind these three different types of memory stores is that the function of memory is to hold information, to store information until you're later able to retrieve that information. And so the idea of short-term memory is that, well, if I read you a sentence, like the one about the good professor, there's a certain amount of time where you're going to be able to repeat that information verbatim. And this is how memory is often tested. This is a test that the people use for potentially detecting some sort of memory loss, like dementia, Alzheimer's. And it's also well known, it's an interesting fact, that one's memory capacity, so the ability to say repeat back, a string of letters or a string of numbers, is actually strongly correlated with IQ. And so there's this idea that there's this thing called working memory or short-term memory, which holds information for a certain amount of time. And the purpose of this the memory store is so that you can go and retrieve that information and repeat it verbatim. And then long-term memory, of course, is just the same kind of basic idea, but just more overall more information. Doesn't have this very limited capacity, and it also can last longer. So at the foundation of the concept, the core concept of memory in cognitive science is this idea of storage and retrieval. That the purpose of memory is so that you can later on get information. Information is stored, and when I say information is stored, what I mean by that is that the way that the information is initially encoded, that there's some perceptual information, some sort of sensory and perceptual information that then it gets stored essentially in its original form, then is kind of like a file on a computer, and then during some sort of cognitive task, when needed, that information is then retrieved. And so the information is sitting there waiting in its kind of original form, and then it's later retrieved. And the most apt metaphor for this, I'm going to close this again because I don't want you staring at the slides. So the most apt metaphor for this, and it's not just a metaphor, it's the way that cognitive science has kind of proceeded for the past 50 years or so, is the computer metaphor. So if you think about a file on your computer, so what's going on with a file, let's say you stored some images, or you've stored a music file or a document. So there's obviously not pixels living in your computer. The pixels are on your screen, but what's encoded on your hard drive is some sort of representation of what the screen is supposed to do. So there's basically the pixels aren't literally in pixel form, but what you've got stored is something that's isomorphic to the pixels. The information, if you know in some ways, if you know how to read off, if you know what the recipe is for taking so the numbers that are written down, you can think about it, or the electrical charge, or however you want to think about the representation of information in a computer hard drive. If you know the mapping, then in theory you could actually go and find that file and know what's in it. You could sort of read it off directly from the hard drive. Oh, this is a picture of my cat, or this is a wave file of my favorite song. And there's actually a direct correspondence between what's recorded and what ends up being presented. So in this case, we can really think in a computer, what we've really got is this very clear metaphor, just like files in a cabinet. You've got files, and they're literally called files, right? Computer files. And the idea is just like you can store a piece of paper in a filing cabinet, and then later on, when you need to go and find that information, you go and you know maybe have some index system, and you go and find that file, and you pull it out, and lo and behold, it's still got the information. As long as you know it didn't get degrade, as long as you're able to find it and you have a good indexing system, then that information is sitting there in cold storage, and you're able to pull it out. So similarly, the idea is that the brain is doing something very similar. According to this basic construct, what memory consists of are something like engrams, as they're called. They can be distributed, they could be maybe localized. Nobody's been able to sort it out. But the basic core idea is that there's information that's essentially in the same form when it comes in. It gets translated into some sort of other form. Of course, it's not light, it's not sound, it's not even the brain activity that occurs when you're hearing light and sound, but it is going to ultimately be something very similar to a computer file. So when you are remembering your mother, or you're remembering a phone number, or you're remembering any fact or a basic piece of information, you know, the capital of Texas or something like that, the idea is that that information is stored somewhere in your brain. And then what you have to do in order to get that information is to retrieve it. That's encoding, storage, and retrieval. So very much like we think of Google as or any search engine, right? You've got information that lives on a server somewhere, and I want it on my computer. I want it to show up on my screen. So I got to go and find it. I got to go seek it out. But it's living there in cold storage. It's the information is in the form that is meant to be ultimately displayed. It just has to get translated. It gets translated from some digital format to pixels, but it's just a translation. So fundamentally, it's the same kind of information. And basically, what I'm here to tell you today is that I think that entire concept, that entire construct, is fundamentally wrong, and that we have a new perspective, and that large language models and transformer models, more generally, not only about language, probably other domains as well. But in the case of language, we already have an actual use case or an actual proof of concept that this form of memory is not necessary. And I would suggest that there are major gaping holes, and that's not only my suggestion, in this entire construct. And so it's not just that we have a positive example of an alternative, but it's that there are actually fundamental problems that have kind of been glaring for a long time in terms of the way we think about how memory works. So one example is just the one I mentioned to you before. What is that kind of memory where we're having a conversation now? I'm talking to you. I've been talking for a while already. It's been, I don't know how long, maybe 10 minutes or so, 15 minutes. You have a pretty good idea, hopefully, if you understand what I'm talking about, of the flow of the conversation. Now that includes lots and lots of words, not just that first sentence that I said, which may still remember the basic gist of, which was like, I'm going to read you a sentence, and then I'm going to test you on it. That informed the rest of the conversation. What I was telling you in that very first sentence was actually something that whose purpose whose existence was going to influence the rest of the conversation, so that even the things you're hearing about right now are being influenced by that very first sentence. And the same goes for information. Oh, lots of stuff that I've said that if I asked you, can you please repeat what I said, 10 seconds ago, 30 seconds ago, 5 minutes ago, you very, very likely wouldn't be able to repeat any of it verbatim. In fact, you'd probably have a very coarse idea of what that information actually consists of, but you understand what I'm talking about. And what does it mean to understand what I'm talking about? Well, you could, if I just said, if I started off this conversation with, you understand what I'm talking about, right? In isolation, that has no meaning, right? You wouldn't understand what I'm talking about at all. Well, when I say you understand what I'm talking about, it's because you are actually living in this cognitive moment that you're living in is actually standing on a much larger structure of information. And that is invisible to the storage, the encoding, storage, and retrieval model. In what sense are you retrieving this information? When I'm talking to you now and you're understanding what I'm saying, you're not retrieving anything. When you remember the capital of France, it can seem like, yeah, I went and I retrieved that information. It was there. But when you're following a conversation, and you can do this for minutes, or you could even do it for hours, I would argue you do it in some sense over a lifetime. We have lots and lots of information that builds over a very long period of time. We're not really retrieving anything. So hole number one is that there isn't really a role and a clear model or mechanism for thinking about information that is not truly retrievable in any sense. It's not retrievable in the sense that you can pull it out like in short-term memory, repeat it verbatim. It's not repeatable. It's not retrievable in the sense of long-term memory that you necessarily remember. You very likely won't remember. Maybe in a year's time, it's very possible you won't remember anything I'm talking about, but you may remember. I'm hopeful that you might remember some of the core ideas. All right, and you may not remember where you heard them. So they become implicit. They become they're no longer retrievable in the traditional form at all. But clearly they're guiding our behavior. Clearly they're guiding our understanding. So there's this gaping hole. It's something I worried about and wondered about for many years, actually, because I always taught this modal model of memory that I showed you that image of. And it's one of the reasons I wanted to show it, because it's in my slides. It's in every textbook. And there's something that always bugged me, which is what happens between short-term and long-term memory. What about all this other stuff? So what I'm going to tell you about today is a completely different way of thinking about what memory is. That's going to account very well for this, and it's actually going to dissolve the entire concept of any sort of dichotomy between short-term and long-term memory. The fact that you can retrieve information verbatim, in my opinion, is just it's just a manifestation of the fact that information is still is fresh in your mind, but it's not actually a different kind of memory store. I'll get to that in just a little bit. But I want to actually point out a couple of other gaping holes in our concept of memory as we've understood it until now. Another one is that there doesn't seem to actually be any sort of retrieval process at all. If you think about, even Google's really fast, right? And if you do a search on your computer, you can find information fairly quickly. And that's because you've got a pretty powerful indexing system that's able to run. But there is still some time between the query and the ability to retrieve that information. And that's for a digital computer that's operating, at the speed of light. Our brains actually are electrical, but also electrochemical, and they're really not that fast. They're not as fast as a digital computer. And there seems to be a mystery in the fact that there doesn't really actually seem to take retrieval doesn't take any time at all. When you're talking about facts and figures, you're retrieving information all the time. You're retrieving information that you need in order to construct the sentence that you're talking about, the information you're talking about, in order to carry on a conversation. There doesn't seem to be any gap of time of retrieval. And furthermore, there seems to be except for those rare cases where we have tip of the tongue. So there was a reason. Tip of the tongue is a phenomenon where you know something, but you don't actually have the information, and that's the rare time where it can feel like, I don't know if some of you remember from the old days when a computer would have a little hourglass or something, and you're still like searching, right? That's this frustrating experience. I'm searching for that information. That is an incredibly rare event. It's rare to the point that we have a name for it because that is, so this outlier phenomenon where you actually feel like you have to search. Now, what you're doing when you're doing tip of the tongue, it can feel like searching, but in fact, that's not really what you're doing at all. We don't have a search mechanism. What we try to do when we have when we have a tip of the tongue phenomenon, like some actor whose name you can't remember or something, is you try to remember things that correspond to, relate to. There isn't actually an indexing system at all. So if there were an indexing system, we might have some ability to search through our memory, but in fact, we don't. And it doesn't really seem to be any sort of retrieval process. Another gaping hole in memory is that it doesn't actually seem to be retrieval in the sense that memory, remembered information and imagined information seem to be fundamentally the same thing. If we look at sort of the brain activity, there's the underlying physiological network that supports remembering something versus imagining something, there doesn't seem to actually be a distinction. And this ends up having massive implications in relation to sort of metacognition, people's ability to judge their own memories. So there's a well-known phenomena that when people like eyewitnesses are recovering information or are repeating information, they will often be subject to mistakes, errors, and also very strongly influenced by external information. If some question is asked in a particular way, there's a famous case. Elizabeth Loftus did a bunch of this research. How fast were the cars going when they smashed into each other versus when they hit into each other? Suddenly, people remember the cars going faster. You can even implant completely false memories into people, and lo and behold, they will believe those memories are true. And the reason for that seems to be not so much that we've been able to implant a false file, and now you're finding that file and you're misrepresenting it and misidentifying it as something stored in memory. It's that memory was never stored as a file in the first place, and all memory is constructed. All memory is really just in time construction, generation of information based on lots of potential cues. And so the blurring of what we call memory and the ability to imagine or to think about or to believe certain things seems to really poke a hole in the idea that there's a fundamentally different system that consists of encoding, storage, and retrieval. Okay, so that's just a list of sort of my, it's the three top reasons to question the fundamental idea of memory. There's one more that's very important, which is that there was an interesting paper that came out a few years ago that summarized that the physiological research on memory, people have been looking for the engram forever. People have been looking for where is the storage happening? Where does this piece of information get encoded? And there's various, there are theoretical ideas of where short-term memory, how that's encoded, where long-term memory is encoded involving the hippocampus, and that there's these sort of stable neural connections that encode information. And the big problem with this theory is that there isn't any stability, long-term stability in specific dendritic connections. if you simply look at the dendritic, the actual neural structures that seem to be involved in a memory consolidation. So you can actually measure these things in a mouse brain. What happens is they tend to drift over time, dramatically, to the point where some people have concluded that we simply can't possibly be encoding long-term memory in terms of our actual dendritic connections, which is was the only game in town for a long time. People have proposed other mechanisms, but this is yet another, coming from a different direction, another reason to doubt the core idea that we have is actually stable information that lives in our brain in sort of file-like form, cold storage, waiting to be retrieved. So what's the alternative, right? I've been talking a lot about, if it's one thing to sort of cast shade on something, but what's the alternative? So the good news is that we have a completely different model that it has emerged on the based on the large language models like ChatGPT, Claude, or whatever flavor of large language model you tend to use. I tend to use a bunch of them. I'm not here necessarily to pitch the use of large language models. People often get confused that I'm very pro AI in terms of its use. I think there's a lot of good utility. I think there's a lot of potential challenges in using it. There's hallucination also. The models have some significant deficits, but that is not what I'm not here to convince you of that. What I'm here to convince you of, I'm trying to convince you of, is that large language models have given us a completely different perspective on what the nature of memory is. I think it extends more broadly to lots of functions of cognition, but memory is a very concrete example of where you can see a completely different model of what we had assumed to be a mechanism being revealed to be something dramatically different. So what is a large language model? So I'm going to show another slide. It's again sparing, but let's do this. Back to my slides. Okay. So we've all heard of it by now. Artificial intelligence is large language models are an example of artificial intelligence. Artificial intelligence was a word that came and went. There were these AI winters, as they're called. There were various different ways that people tried to get machines to do the kind of stuff that humans can do, to be able to see and to be able to think and to play games and to reason and all of that good stuff. And nothing worked. Really, fundamentally, nothing worked until one thing and one approach actually did, and that is neural networks. So this is more recently called deep learning. When I was in graduate school, it was called connectionism. Mostly, I heard about connectionism in the context of the idea of the claim that connectionism was never going to work. It's taken on various different forms and names. Partially, the reason it's taken on different names is people have to rebrand it because the early versions got a bad rap because people said they're not going to work. And that's because they really didn't quite work. They worked for very simple toy problems, but they didn't work to solve real life, uh, actual useful problems that people wanted to solve. So regardless of what your definition of artificial intelligence is and what counts as AI, some people say it's whatever computers can't do that humans can or something like that. But by now, if you are talking about AI, and I don't want to, cast shade on anybody who's consider themselves an artificial intelligence researcher but isn't using neural networks. But if you're not using neural networks, you're probably not doing AI or what most of the world means by AI, because neural networks ended up solving the basic problem of certain, I guess you could say, a certain degree of core functionality that we would call human intelligence. And most of us are probably familiar with one particular flavor of neural network, and that is the transformer models that ended up being the particular way to take these kind of models and get them to do language. And if you hadn't heard about AI and you hadn't heard about neural networks before ChatGPT came along, by now you have. And I've been kind of almost flabbergasted by the way almost every person, every kid now talks about AI. AI was this term of art that it was almost something embarrassing. You didn't even want to mention that your research is in AI because it was generally considered to be kind of a failed thing. It's like, I don't know, like cold fusion or something. Like, okay, good, they had it was a good shot, but it wasn't going to work. And now it's just ubiquitous. Do you use AI for this? Do you use AI for that? Right? Or chat? And now it's just chat. That's sort of the term that kids use and generically, and that is sort of the pinnacle now of where these neural networks have actually shown themselves to be useful. But they're useful for other stuff too. So I want to just give a very quick primer on what these things are and also what happened that allowed them to end up being so successful in doing this very useful thing that we call talking and reasoning. And all of that's going to be a way to get to the idea of going away from the storage and retrieval model and heading towards what I call a generative model of memory. Okay, so what's a neural network? So a neural network is really a mathematical object. You can build it there's lots of different ways you could theoretically build it. We mostly build it in digital computers. And what you can think about it is just a sequence of mathematical operations. And it has to be sequential. It's kind of really important. You do a mathematical operation, and that if that doesn't get you excited, a sequence of mathematical operations, I don't know what's wrong with you, right? That sounds horrible. So let's make it a little more concrete. What do I mean by sequence of mathematical operations? It turns out it's going to be really simple. That's the beauty of it. These aren't fancy operations. So it's things like this. So we have an input layer. Whenever you see a network, you're going to see these kinds of layers. So an input layer, what we think of that is just some sort of way of encoding your data, something about your data. So what do I mean by data? Well, let's say it's an image. Let's say it's a picture. I like to start off with pictures and images because, William Hahn was on I think in the audience. Well, we always talked about the cats and dog problem. And the cats and dog problem was a really hard problem to solve. You take a bunch of pictures of cats and dogs, you digitize them, and then you ask a computer to tell you, is that a cat or a dog? And forever, the computer's going to do it. And it seemed really stupidly simple, right? Kids can do it. Why the hell can't the smartest people build programming computers? Why can't they do it? And the answer was because they were trying to program the computers. Turns out that's not how you do it. What you have to do is you have to come up with a process whereby the computers can kind of anneal to a solution. You have to give them a learning algorithm where they can come up with a solution rather than a really smart human saying, here, I think this is what the solution is. So let's think about an image, right? You got a picture of a cat. You can think about that picture, like we were talking about pixels earlier, as a bunch of numbers. And so those numbers represent, well, what do they represent? In some ways, they're sort of just numbers. They're numbers stored they can be numbers stored on a machine. Those numbers can be used to light up your screen, right? They could be pixel values, which is really one way to think about them is that they're going to tell you the red, green, and blue values for your pixels. But when we have an image of a cat, in some ways it's abstracted away. This is like the file conversation we had earlier, and what you've got is a bunch of numbers. You can take those numbers and you can feed them into a neural network. And what to feed them in it really just means is we're going to put those numbers, we're going to represent them here in this input layer. We're going to have, here's one of the, it happens to be red, so let's think about this as the red channel. You've got 54 and 23 and 69. Now, how you represent that, it's a bunch of strings, it's a bunch of zeros and ones. It doesn't really matter. As long as you have consistency, right? As long as there is some structural relation between these so that these are basically the right distance away so that you could think about if you were making pixels, it would be how red is it? This red. And how red is this part? This red. And so basically what you've got here is some numerical representation of your data. So it could be a picture of a cat or a dog. It could be lots of other stuff too. It could be, something about the weather. It could be some sort of sound file. As long as you can turn that information into a numerical representation, you can feed that into a neural network. And what does that mean? Feed it again? It just means we're going to put those numbers here. And then what you do is you take those numbers and you do something with them. And in the case of neural networks, generally what you do with them is you just multiply them, right? So not so fancy, right? You multiply them by some numbers. So let's say we have this particular pixel value here in this guy. And then what we're going to do is we're going to multiply that pixel value by some number. And here's another little arrow, and we're going to multiply by this number, and we also multiply by this number. We're going to keep track. This number is going to get represented over here. We're multiplying this, multiplying it by a certain value, and then it's going to get represented in this thing over here. This one's going to get multiplied by a different number. It's going to represent over here. Okay, so we're feeding forward these numbers, multiplying and feeding them forward. And then what we're going to do is we're going to aggregate. So like here's a bunch of pixels, and we're multiplying by these numbers, and we aggregate them. And then we do this nonlinearity. Okay, we're not going to get into today why exactly need a nonlinearity, but that's super duper important. It's the reason why layers matter. It's the reason why neural networks can do sort of very nonlinear, sort of nonlinear problems. It's why they can do things closer to categorization. In any case, this is the math. So what I mean by nonlinearity, well, that sounds fancy. And nonlinearity can be a cool a very complicated sigmoid function or something like that. But in the case of neural networks, it could be really something stupidly simple, like anything below zero, we're going to call it zero. Anything above zero, we're just going to use that number. That's the rectified linear unit, which is a fancy way of saying just what I said. Okay, so we're doing these mathematical operations. We're taking a bunch of numbers. Those are your inputs. Then we're manipulating them by some numbers. We're multiplying them, and then we're doing some nonlinearity, and then we're doing it again and again and again, right? Usually they have lots of layers of this, and then we have some output. And the output here could be some number that represents, well, what you think's in the image. Let's pretend like these numbers here, there's some numbers in the output layer, and those numbers, if it's a 0 here and a 1 here, that's a cat. If it's a 1 here and it's a 0 there, that's a dog. And so what we want is for this machine to take in the right input and take in given input, produce the right output. Awesome. How do we get it to do that? So what we don't do is sit there actually saying, what should we multiply this thing by? That's never going to work. Instead, what we do is this learning algorithm. There's a way to use the magic of calculus to be able to get these systems to actually figure out what these parameters or weights are supposed to be. Now, we're not going to get into how any of that works, but what I want you to see here is by the time you've trained this thing, what you've done is you've given it a recipe that's encoded within these weights to take a given input and arbitrary input. So you can give it a picture of lots of different pictures of a cat, lots of different pictures of different kinds of dogs. And if it's well trained, it's going to be able to produce the right output. And so at this point, we could actually think of this as a function, right? Formally, it is a function. You put numbers in, you get, whatever number you can put arbitrary numbers here, and you get some unique. For every input, there's unique output. There aren't two different outputs for any given input, so it's a function. It happens to be a function that maybe recognizes cats and dogs, but it could do lots of other things as well. And so we can think about this as sort of at the heart. This is at the fundamental heart of every single AI application that you've seen today. If you're talking about self-driving cars, if you're talking about medical diagnosis, if you're talking about language. And now language is going to be the interesting one, and we're going to talk about this in a little bit more depth. How do these things solve language? What would that even mean in the case of language? And this is where sort of the magic happens. And it's in the title of my talk. I'm going to stop sharing this because I think I don't need to show you that image anymore. So what we've got here, what we had since maybe circa 2013 or so, was a very successful example of neural networks doing real world stuff, cognitive stuff that kind of looked a lot like what the human brain does. Take real world data, things that are very messy. There's no structured solution. You can't write down a recipe for how you recognize whether a cat is a cat or a dog is a dog. How do I know? Because again, the smartest people, we got to the moon, we built nuclear bombs, but nobody could figure out what the recipe is for a cat or a dog. And it's because there really isn't a craft. There's no way to write that down as a set of rules. Instead, it simply has to be there is no greater there's no greater simplification of it than these kind of weights in these models. Now, we've moved now from images to language, and the question is how. What's the challenge, and what was the solution? And that's where so again, I myself was paying very close attention to what was going on in say 2013. And again, William Hahn and I were both kind of bugging out and saying, "Wow, these things are actually really smart. It's working." But most of the world was like, "Cool. And in fact, we spend a lot of time actually trying to juice people up about this and say, hey, this is really important. Look, it can do all kinds of stuff. And they'd say, like, what kind of stuff? And we'd be like, well, it can do image labeling. And they'd be like, "Yeah, okay, that's, I guess that's interesting and important. But the applications of image labeling were kind of limited. We're like, well, it can do MRI, it can do cancer diagnosis, which that's really important. But that's a very restricted kind of application. And furthermore, from my perspective, I was like, is this the brain? A lot of people are like, well, no, our brains do a lot more interesting stuff than just labeling whether something's a cat or a dog. It seems like a very narrow scope. Now, what happened, of course, is we had the arrival of the transformer models and language. And language is suddenly similar. We had image labeling was solved, but people are like yawn. Image generation was kind of pretty darn cool. You could say here's some sort of verbal description, and you could output an image based on that, kind of reverse captioning. And that was interesting, kind of cool. You could show people that they'd be like, "That's really awesome." But what's for lunch? It didn't change their world, right? What changed everybody's world to some extent was the ability to use these things to do language. So how does that work? What does it mean to use these in order to do language? And wherein lies the difficulty? So when we're talking about language, what does it mean to use a neural network to actually understand and produce language? And if you think about it, you might just find yourself scratching your head, because what I said was it's an input and output. It's a neural network is just basically a function. What that means is you have a given input produces a given output. In the case of images, great. Here's you got you pixelize you digitize your pixels. You've got an image, and you want an output that's a label. And okay, cancer, not cancer, dog, cat. That makes sense. I can see how that's a function. But language, what does it mean to say language is a function? What would that even mean? So you could think about, so by now you remember what that neural network looks like, but you think about what would you put on the input side. Now you could imagine giving it like a sentence on the input side. Maybe it's like the sequence. You put it each little node gets something like a word. Um, and then and that makes sense. And in fact, that's essentially what we're going to end up doing. You're going to say each node is going to take in some sort of digital form of a word, some sort of numerical representation of let's call it numerical. The digital is not even the point, right? So numerical representation of a word. And then what? What do you produce on the outside, on the output? And so uh, the answer is actually quite surprising. And to me, it was astoundingly surprising. This is the sort of the mathematical result that shook my world. And that is what you're going to do in the case of language. Well, okay, let's just speculate because maybe you're thinking about it now. Maybe right, sort of the answer to this question. But if you think about what you might want on the output, well, you may think, okay, give it a question. Here's a prompt. Write me an essay for my, I'm a high school student. I have an essay to write about the American Revolution and its cultural representation in modern in the modern culture, something like that. And just to jog to get the intuitions going. Not that I'm actually going to hand in my ChatGPT report, but let's just say I want to get something out on the other end. What you can imagine doing is you've got a certain size of input. Here's the question, here's the prompt, and you put a bunch of numbers in there, and then on the output, you're going to have maybe the essay, that comes out and that's the function. But that's not how you do it. That's not what works. And part of the reason that doesn't work is because you want to have a really arbitrarily large outputs. If for a given prompt, let's say, write me an essay of blah, blah, blah. Let's, it could be, the prompt itself could be a few sentences long, maybe a paragraph long, maybe it's even longer. In theory, if you allow these models to run, they can answer that question in very long form. They could respond in, as we can. If you don't believe me, just look at me, right? What was the prompt of my talk, right? I could go on and on forever. I think you've already gotten that impression, right? So there isn't really a fixed output size that you could say, I want to get from this input, I want to produce an output. What is the solution to that? There is no function that's going to solve the problem of language. There's another problem, which is that the inputs are can also be really, really large. And yeah, this actually haunted the field for a long, long time. That the inputs that you really want to go into a language model can be, as I said, paragraphs or like book length, right? If you really want to be able to, if you want a large language, any sort of a computer model to be able to answer questions as a human can, well, you have to be able to read the novel, and then we can discuss it, right? Even if you don't actually read the book for your book club, you want your AI to be able to kind of read information, ingest it, and produce the appropriate output. And so the size of the input is a very significant problem. But the even bigger problem is the arbitrarily lengthy output of language. And so we see this in human language, right? If you ask a question, the answer is usually going to be much longer than the question. So how do you solve that? And so the magic is this thing called autoregression. And for those who know me, I don't know if Eddie's out there somewhere. It's like the old joke. How do you know a Harvard man? He'll tell you. Well, how do you know that I like autoregression? I will tell you. I am always going on and on about autoregression. And that's because to me, it was sort of this mathematical realization of sort of a completely different computational framework that changes how you think about what knowing is and also what cognition is. Okay, so the answer to the question of what is the function that a large language model is actually computing is all it's doing is what's called next token prediction. I don't like the word prediction. It's not quite the right term, but that is what it's usually called. So what's happening is you give it a sequence, and the sequence can indeed be very long. And that's part of what makes large language models large is the fact that they're able to take in very long strings. It's not really why they're called large language models, but fundamentally it kind of is because they have lots and lots of layers and stuff. But the reason they need lots and lots of layers is because they can take in very long sequences. And that the context size, as it's often called, is getting bigger and bigger. By now, Gemini, which is Google's large language model, I think they're currently leader in the pack as to how many words it can feed in. But on the output side, actually, the output is very low dimensional. It's just a single token. What it really is, if you want to get into the nitty-gritty, it's a distribution over token space. It's basically saying which token, like forget token. I don't need to use that word because people get confused. Let's just call them words. If you want to talk to me later about whether tokens are words, okay, they're not technically words, but they're approximated by words. They're chunks of things that sometimes they're words, sometimes they're like suffixes and prefixes, but whatever. What the thing is doing, what the large language model is doing, is it's guessing the next word or piece of a word. And so that's a very low dimensional thing. And like I said, it's the distribution. It's saying which word how likely do I think the next word is this? So some particular word, how likely do I think it's some other word, and you get a distribution. But that's all they're doing every time, every pass, is they are producing just the next the guess of what should be next. So when you ask it a question like, when you give a prompt, write me an essay about the American Revolution and the cultural impacts and whatever, all of that whole string, it's going in, and what it's doing, it's running all this magnificently complicated trillion parameter, neural network, right? All those little weights that have to get learned. It's running that magnificently complicated system just to say the. And that's it, right? The American Revolution, right? So here's what happened. What is autoregression? So autoregression is that you're doing this regression. So you're regressing, kind of like when we think about predictive modeling, regression, like a linear model or something like that. Don't worry about it. It's not linear, of course. But what you're really doing is something like prediction. You're saying here's a bunch of values. The values are the input values, and they're given those values. What is my output? And the output here again is going to be distribution, but we can think about it very simply as what should be the next word. Okay, so it says the, and then here's the magic, right? I'm like, wait, what do you mean? That's not a good answer, right? That's very disappointing. If that's all my model did, I'd be like, well, that's I'm not going to invest in OpenAI. Well, they're not public anyway, but that wouldn't, look, it got the right next word. Nobody would care, right? It's kind of like image classification and labeling. Nobody really cares about low dimensional outputs. They're of limited utility. But what you do, here's the magic, right? You take the, and then you stick it back into the model. And it says, here's the whole prompt. And you stick it back in the model. What do we mean? Just tack it on to the sequence. So you have the prompt. Write me an essay about the American Revolution, blah, 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 the. And that goes back in. It feeds itself. I don't know. I haven't come up with a better metaphor yet, but like it's like like eating your own spit or something like that. I'm sure somebody can give me a better one after this talk, please, because I don't like that one at all. But it's outputting and then it's feeding that output back into itself as part of the sequence. So it's got this very long sequence, and then it's making that sequence one token longer. And guess what? Here's the magic. The magic is this function is infinitely flexible. It's infinitely flexible, meaning you could put anything in there. You can put, whatever sequence you want, and it can be a sequence that no one has ever produced before, and it will produce something that's reasonable in terms of that next output. And so what this thing is doing, it's sort of self-dealing. It's feeding itself back its own output, and now you've got a new input. What's that new input? It's the input that's premised on the fact of its own output. And then you just do this recursively. You iterate through this, and that's the autoregression. When you see those language models run, you especially see it in the old days, you still see it. They generate like this. They like, and it looks like it's kind of just being cute. Like maybe it's just like sometimes you see like visualizations that are supposed to look like an old-fashioned computer, and it's kind of rastering and printing it out. But that's real. That you're seeing it think in real time, because what it's doing is it doesn't know the answer to what the fifth word is. It doesn't know the answer to the 10th or the 100th word is. Instead, it only knows the answer to what the next word is, and it's taking that word and it's putting back into itself, and then it's running itself through. So here's the crazy thing, right? You've got here is a function, right? The function is just to input, single output, but within that capacity to do this input output, that single output is the capacity to generate these long form responses, and it can seem like magic, because how on earth does the predict what's going to come down the line? Doesn't it know when it says the importance of culture in the American Revolution? Doesn't it know that it's going to be talking about the American Revolution when it starts that sequence? And the answer is no. It doesn't actually fundamentally know that. It's not answering that question. It's not thinking about the future per se. Well, then how the hell does it work? Right? That's the big question. How could that be? And I promise you, when I first heard that that's what was going on, I was like I thought I misheard. How could that possibly be? And so this is the magic of autoregression, is that if your information that you've learned is structured in such a way that there is a predictive structure, so that you've got a sequence, that sequence not only predicts what's going to come next, but it inherently contains within it, not that the model is doing this, but the sequence itself contains within it the information that's necessary in order to predict much further out. So what's one way to think about this is it's fundamentally doing next token prediction, but that the data that it's learned in order to do that next token prediction, the data contains within itself this long range predictiveness. And this was sort of a crazy epiphany number one for me, was that language has this predictive structure built within it. Because all of that these large language models do is churn through the relational structure, the topology of the sequence, of language sequences. They don't get any other kind of information, which means that the information has to be in there. The predictive information has to be already within language. And it's not only that here's why it's not prediction. It's not only that you've seen this sequence before, tell me the next output. It's arbitrary sequences. Anything you can come up with, if there's a reasonable output and a reasonable response that makes sense in language, these models can do it. Okay, so what we've got here is this sort of magic of a recursive and implicit inherent structure in language that allows these models to generate now, and they're generative models. Why are they generative in the sense? Because they're not only doing something like labeling, They're not just doing a single output, even though on any given turn, you're just running that single function. It's a static function. It's not changing as it's generating, right? What it's doing is the same function, but it's now getting different sequentially, getting different inputs that are running through it. And but when you run it auto-regressively, you actually get generation. And generation here means that you're getting output structure that's of similar complexity, richness to what goes in. Actually, in some ways, it's even higher, right? So, in other words, it's language in and it's language out. It's not image in and label out. It's generating exactly the same kind of information, the same kind of data structures as what goes into it. Okay, what does any of this have to do with memory? And gosh, we're pretty far along. So the answer is it all has to do with this flexibility of these models, and it has to do with the way that they're generating. So if we think about, so if you ask a large language model, tell me the Pledge of Allegiance, can it recite it? And the answer is yes, it can recite the Pledge of Allegiance. If you ask it to tell you about the American Revolution, it can tell you that information. Are there n-grams in these in the transformer neural networks? Could you look, remember we talked about the computer files, that if you know the translation, you know the mapping, you could go and find and figure out without sending it to your actual monitor. You could say, oh, I have a translator that I can find the presentation on my hard drive, and lo and behold, that's my cat. I don't have a cat, but that's your cat. Okay, it's there. Can you find the Pledge of Allegiance? Can you find the answer to the question of what were the cultural influences that led to the American Revolution? Is that information in there? And the answer is no, it's not in there in the sense of storage and retrieval at all. The information simply isn't in there. And what I mean by that is if you ask it to recite the Pledge of Allegiance, you can't, God's, engineer himself, if they had, there is no mapping. There is no mapping that can go from the state of those weights, those dendritic weights, to the Pledge of Allegiance. You can't get it. The only way to get it is to run it. You have to run that function, and you have to feed it back through. So the information simply does not exist in static form in these models. In a nutshell, what I've been trying to convince you this whole time, what I'm trying to get to here, is that that's how the brain works as well. That we ourselves do not have information contained in sort of static form that we are going and retrieving. Instead, what we're doing is running some sort of autoregressive model in neural tissue. That is my claim. Now, the basis of my claim is I probably don't have enough time. I don't know what time we're going to. But the basis of my claim is that there's lots and lots of similarities between how large language models operate and how the human brain operates. I mentioned some of the reasons why I think we should be skeptical of our version of how memory works. By the way, those skepticisms they dissolve in the face of thinking about memory this way. If one way to think about this is that what memory is generative influence. Now there's a state of our brain at any given time, right? And it's just like the dendritic weights in a large language model. And what that means is but the state doesn't really correspond to a set of facts. Instead, what it corresponds to is a propensity to respond to a given input in a certain way. As I said, you can ask the large language model whatever you want. You can have that cat and dog function, right? The cat and dog recognizer, and you can give it an image of anything. It's going to produce something. It's going to produce an output. Functions are, these functions are infinite in terms of the possible space of input and outputs. You give it as many inputs. Well, that's how many outputs. They're not really infinite because it's not continuous, but whatever. We could think of it, it's functionally infinite. And in the case of information stored in our brain, what it means to know, like what about the American Revolution, or to know what the Pledge of Allegiance is not to have that information stored there. It's to be able to respond appropriately in this autoregressive fashion to the appropriate prompt. And that's sort of the magical flexibility of language, the thing that everybody worried about, like how the hell does this work for so long with this productivity feature? How do you get infinite flexible outputs? Well, now we built it, and it works. And the answer is you don't store facts, right? If you can't, you can only store a finite number of facts. And if you have too many of them, first of all, it's going to be hard to find the right one. And second of all, you run out of, you can't, or you'll never get to all of them. But if what you have is this generative capability, then basically what you have is an infinite fact producer. I can ask you, if you know just a couple of pieces of information, let's say, where do you live or something like that. There's many implications, infinite number of implications about where you live, because it's where you don't live and where you live next to, and who else might live there, and where are you going to live there forever, and blah, 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 right? There's just so many possible implications of that. And if you think about it, it seems overwhelming. How could we possibly represent that information? Well, we have, as I said, we have a proof of an actual system that does this. So the structure of language itself is infinitely generative. And so that's what we're seeing in these large language models. And my claim is that human memory is operating, human knowledge and human memory is operating the same way. We don't store information. And the reason why information is so malleable in memory is because what we're doing at any time is really just flexibly generating. The same way you can answer very many different versions of a question about some specific piece of information, that's a feature, right? Not a bug. If you say, I know this concrete fact, well, then all you've got is one single one-to-one mapping between a question and answer. That's base memorization. We all know that's a very limited form of knowledge. What you really want to be able to do is talk about the thing, and talk around it, talk about it in different ways. That kind of flexibility is you have this kind of infinite productivity, is sort of the hallmark of a non-storage and retrieval kind of framework, but a generative framework. And so the seemingly unsolvables ended up not only being solvable, but sort of pointing the way to what I think is the solution. That we're not doing storage and retrieval. What we're doing is, I call them, I can't remember. Isn't that amazing? And I talk about memory, right? Finding that exact words, because sometimes I haven't used this word in a while. Potentialities. Potentialities is a term I sometimes use for this, right? You've got this system, and it can, you can give it this input or that input, and then an infinite number of possible inputs, and it can produce appropriate outputs on the basis of that. And so if we think about memory that way, and we can move beyond the storage and retrieval model. And by the way, this is not just about language. I think that this probably applies to other forms of memory as well. So what does it mean to remember where you left your keys, or to remember, what your childhood friend looks like? Right? So the old version would be like, you've got a sort of image of your childhood friend, and it's stored somewhere, and now you retrieve that image. But the thing is, I think we all have an intuition that that's wrong, because you can remember your childhood friend doing just about anything. When you think about that, every single time you think about that childhood friend, it might be in a different context. And if you're reminiscing about that time you did, X, Y, or Z, that image is going to be completely different. Remembering where your keys are, it can seem like you've got this sort of stored visual memory, but which angle do you remember where your keys were from? And here, so I have a lot of difficulty often remembering where I leave things.
Elan, we have to
Yes,
remember one thing.
yes.
It's 7:12,
Oh
and
gosh.
the talk it's going amazing, but I think we have enough questions, and I'm sure a lot of the audience
Okay, I'm almost
want to
done. I really
interact
am.
with you, right?
I'm
They want
almost
to
done.
pickle
I'm
your
almost done.
brain. So how
I'm
about
almost
we
done. I
start with some
appreciate
of
it. I
the
appreciate that.
questions,
I
and then
couldn't
we can
believe the
make it a
time.
little bit more
Okay,
dynamic.
got you. I'm pretty much there. And I only talked
Don't
about like
leave.
one.
You
I
have a
talked
lot
about
of
1/10 of what
questions.
I wanted to talk about, but I just wanted to say that this extends to other forms of memory. And so remembering where your keys are, what happens when you remember your keys are, you're not like retrieving that piece of information. Your brain, and you try this next time you think about where something is, your brain produces the image in your head. And it's like, oh, that's what remembering is. Like suddenly you see them in your head, and you're like, yeah, oh, yeah, that's where I left them. It's all it's doing is generation. It's not retrieving. So this I think applies to lots of different kinds of memory. And basically, this is, as I said, a radically different way of thinking about the nature of memory, the nature of cognition. But I'm out of time. And thank you Natalia, for jumping in there. I obviously could have kept going for several hours without realizing it.
I know
So
you're
thanks for
dangerous.
those who
Yes,
stuck
but
around.
let's interact because I think we have a great audience over here and there's a lot of questions. So I let you guide the discussion for those questions, and I'm going to ask to try to limit your answer between 2 and 3 minutes
All
per
right, can you
each.
moderate? Do you want to call on people?
Sure. So let's see. First question, how do you train an autoregressive model?
Auto-regressively. No, actually, you don't train it auto-regressively. That's the cool thing. So the way you train an auto-regressive model is just by asking it to do the next token prediction. So you just say, here's a whole bunch of language. And the beauty is that like we've got lots and lots of digitized language. It's called the internet. Almost like the internet was like the perfect storm that you needed in order to train these models. And so what you do is you just take digitized text, and you send it's like just like that neural network we were looking at before. You encode the text. There's you turn them into tokens, whatever. It's just a numerical way of representing each little language chunk, and you give that sequence. You give it a sequence, like here's a prompt, or here's a paragraph, and you literally ask the model to guess what is the next word that's actually in the data set. So you can imagine, right? You've got huge amounts of data, and you could say, here's 10 words, give me the 11th word. Here's 100 words, give me the 101st word. And you just do that over and over and over and over again. You don't actually train them autoregressively. They don't actually take that sequence that they've produced and then feed it back into it. All they ever do during training is just do next token prediction. It's as simple as that. But how does that possibly work? And the answer is because they learn these contingencies. They learn that for a sequence that's paragraphs long, this is the very next token. It's mind-boggling that that's how it works, that all they ever can see is that very next guess. But that is sufficient to learn the structure of very long form language. So that's it. That's how you train them.
That's great. Alan, does that answer your question?
Yeah. So they get the training is at each discrete step
Yep.
in the process.
That's
Is
it.
the adjustment of the weights and parameters, etc.
Exactly. So he guesses the next word, and then we're like, "How'd you do? Oh, wait, you got it wrong. Let's adjust the weights to do better, get closer to the right answer," and then you do that. And so with neural networks, what you're always doing is you're doing this iteratively. The training process is this. That's the real computational expense is actually in the training. It's figuring out how to set all those weights, and you're doing it iteratively. Like you're saying, "Oh, how'd you do? You guess, you're off by a certain amount." You can figure out how you have to change the weights to get closer to the right answer, and you just do this again and again and again until it gets better.
Randall, are you there? Randall is asking, is autoregression Bayesian or backpropagation?
I'm sorry, is autoregression, what was the first thing?
What is my first name? Is that what you said?
No, I
No,
asked you.
Randall, if you can repeat your question.
There were two choices. Is autoregression something or backpropagation? I didn't hear
Bayesian. You mentioned you were adjusting the nodes, so that sounds like backpropagation.
It is.
But at first you were saying you're predicting the next step, and there's a prior. And
Great question. Great question. So there isn't actually, yeah, it's not Bayesian, and there is no prior really built in. What's happening is just backpropagation. So this is a supervised learning, and what all it has to do, as I said, it's taking a sequence to produce the next member of that sequence, and then you're able to measure how much each weight was contributing to the incorrect answer, and then you adjust the weights through backpropagation. And so backpropagation is this amazing capability. You could do it. I have to mention automatic differentiation. You can run calculus on these complicated these loops that are in the model. All of it's a neural network though. It's really just about these dendritic weights, and all you're doing is just incrementally changing those weights so it gets closer to the right answer. During training, it gets the right answer. Here's what you should have guessed. But there's no Bayesian priors.
I work in natural language processing, and this is even confusing to me because, like, when you're sending an email and it's predicting the next letter in a word,
yes,
or the next word, it's actually not looking at semantic content. It's looking at binary code. So if you push T and it says the next letter is H because D is a common word, that's really not deep learning. That's more, seems more Bayesian to me.
Well, they don't operate at the letter level. First of all, they operate with kind of larger chunks, and so it's really trying to guess something closer to the next word. But it's really just doing that entirely based on the internal structure of, so as I said, the topology of language. It knows that given this sequence and these relations between these words within the sequence, that is the next probable token.
But it's still right in the middle because you're not really looking at the semantic content and meaning and reasoning and common sense. It's just,
You bet. That's what blew my mind more than anything is that the language itself seems to operate independently of any grounding. There is no semantics outside of just the topology of language itself. And if that doesn't blow your mind, well, then you either haven't understood what I've said or you are, very unperturbable because that is absolutely, it should make you crazy. How does language run if it doesn't mean anything? But yes, that is actually a corollary finding here of the large language models that language can operate without any reference, any external semantics, any sort of world model, anything like that.
in what we do, like deep learning is not actually reading. It's like the semantic web. All these words are turned into numbers and vectors, and that's what it's reading.
That's right. That's it. And in fact, in one way to think about what it learns is a very hyperdimensional space, and where each word, each token lives within that space, and the relational structure of where words live next to each other, that ends up being, in essence, what it means to know language. Is knowing this relational structure. Nothing else, right? It doesn't correspond to anything outside of that. The space is just where tokens are in relation to one another. That is the sort of the actual essence of what ends up being learned in a large language model.
Well, I'm glad to hear that because if you actually understand what deep learning is at a fundamental level, this doesn't really fit into it perfectly.
Well, again, it's just back propagation of a neural network, and so that is deep learning. It's a multi-layer neural network that is every single flavor of large language model is ultimately a part of the family of neural networks, and it's a multi-layer and trained through back propagation, which is I think the working definition of deep learning. So it is
Well,
deep
it
learning.
just has more layers and more parameters than what I do. So
Well, we can debate this whether you think it corresponds to deep learning, but I'm sure there's I don't know if Dugan.
Well, the corpus of text that LLMs were trained on was encoded using a world model.
Yes.
So,
And this
like
is
the fact
often
that the sky is blue is this empirical fact about electromagnetic radiation doing its thing, and Rayleigh scattering. And then that fact is encoded in language syntactically as sort of the sky is, and then the word blue is follows. And then that sentence is sort of repeated a lot in the training data, such that it got encoded in a vector format as this like relationship between the words the sky is and then the next token blue.
absolutely
So like, blind people, like I like to say this, that blind people, they know that the sky is blue also, but they don't ever see it. They just hear other people talking about it.
right.
And so
That's exactly right. And of course, language didn't get its structure from nowhere. It got its structure from the world, and not only from the world, but from our sort of interoperability between other people and our with the world and all of that stuff. But it is still a shock that it can ultimately still operate. That's how it's got its structure. But once it got that structure, the structure runs itself, right? So that it can answer any question without sort of in any way querying or influenced by the world, right? It's like the world is somehow actually encoded in some sense in the linguistic structure, but the way it runs computationally doesn't actually require anything outside of itself. I refer to this, that's an auto-generative property of it, that it's just the topology that ultimately does the work. Now, the fact that that ends up corresponding to the reason why this, it wouldn't be cool if language, didn't have meaning, right? It does stuff. Like I can say to you, could you go grab that, could you turn on the lamp behind you? And it has very clear structural relationships to behavior and the world. Of course, you could produce any sequence. That wouldn't be impressive. It's that these are meaningful sequences, and meaningful ultimately means that it has this function in terms of communication and things like that. But in its core, in its guts, it is actually just running purely topologically. It's not actually
Right,
in
right.
any way.
No, it's amazing and it's fascinating. It's just yeah, there's a morphism between these syntactic structures and then the outside world which they're trained.
And it's not
to-
even with the world. That's the crazy thing. It's like, no, it's like how operate within the world and communicate. Like it works, right? And so it's a much looser kind of thing than even saying the world is there. It's like, we got to think, we have to rethink all of what we think language is. And that's, today I was talking about memory, but really the thing that I've been spending most of my time thinking about is language and what the hell it is now that we see it's something else.
Yes, and we're going to have a second talk with Elan in 2026, going a little bit deeper in what his research is about, right?
You bet. I think I have some proof about this this auto-generative structure of language. Something.
But in what you're working with, are you actually looking at the semantic content, or you're looking? I don't know what you're looking at.
Well, I haven't really told you much about my own research. I could tell you a tiny bit about that, but so my research there's two pieces of it. One is trying to actually determine whether the computational structure of language, what is that computational structure, and what does it mean that transformer models can learn it. So a really quick hint at that is the transformer models can't. This is something I hope to publish soon. They can't learn rule-based systems at all. They're really bad at it, like Fibonacci or some very simple rule. If the sequence is generated by a rule, they're really bad at learning that. It seems like language itself, I think we've discovered something about the nature of the language itself, that it's meant to be generated based on its distributional structure. So Chomsky was wrong. There's no syntax. There's no external rules to how you generate language. That's one piece I'm working on. Another piece is actually looking at human memory and trying to model it. Not even model it, actually. That's not the right word. Human memory to use transformer models and to see whether we can actually get similar kinds of performance differences that you would predict in say human pathology. So, like for example, if you ablate the self-attention, which I didn't talk about, I didn't have time to, but if you kind of modify the self-attention, do you see things that look similar to what you see in cases of memory loss? Because my theory again is that memory is generative. It's not about what you remember or not, you can retrieve, and like through standard memory tests. It's that I would predict that you're going to see like generative issues in the way when you see memory deficits. I think it's going to show generative issues. So I'm looking at sort of human correlates of the computational model, and then I'm also looking at the actual computational structure of language through these transformer models.
But that's like the second question I asked. Maybe we'll get to that later.
Well, I got time, but
yes.
I want
So
to.
before we go into like more of like those questions, so before we go into those ones, let me reorder these. So the LLMs operate in discrete tokens with fixed embedding, brain does not. How do we reconcile these two?
Sorry, I couldn't. Can you repeat it? I didn't
Yes,
realize.
LLMs,
Okay.
they
Yes.
operate in discrete tokens with fixed embeddings, and brain does not. How do you reconcile these two?
Good question. So do I think that there are, would I propose that there are something like discrete tokens in the brain? Well, so this comes back actually to one of the earlier points I made about the fact that the representation information in the brain is not as stable as we might have thought. I don't think that there's anything like very discrete tokens, but I think so My theory is that there's a very strong computational core computational equivalence between it's sort of the next token generation and the way the brain is doing generation. But that's as far as I'll go, in the sense that I don't have an actual claim about how the information is represented neurally. I have quite a bit to say about the neurophysiology and what I think might be a direction to think about at the very macro structure, like feedback as contextual representation and things like that. But in terms of how does the brain and neural states, is it dendritic? Is it actually even, at the activation level? Is it maybe at the population level? I have no idea. I don't have anything really sensible
Okay,
to
so
say
that
about
kind of answers if we have any evidence from behavioral science or neuroscience that support the autoregressive architecture. So
I got a
are there
ton.
any papers that are pointing into that direction?
So I think we've got like 75 years of evidence for it, in the sense that there's many, many phenomena that are better understood through the generative model. And I've got this big fat volume of stuff. I hope to be releasing this on archive soon, and submit it for publication at some point. But I think there are many, many facts that point in this direction. Some examples that I already shared are things like the reconstructive sort of the constructive nature of memory, but things like garden path sentences, where you see that sequence really matters. We end up committing to a specific sequence, and we can't pivot away from that sequence very easily. So the linguistic, I don't know if you don't know what garden path sentences, I don't really have time to get into it, but it's where you end up sort of doing the wrong next token prediction. It's like a very a clear example of it, where you're expecting something in terms of what trajectory the language go, and then you're wrong, and people have they can't figure out what's being said. So the classic example is the horse raced past the barn, fell, and you get to that fell, and it doesn't make any sense, because the horse raced past the barn. You have a certain sort of trajectory of what the prediction is going to be, and then boom, you end up with the wrong prediction. You're like you're in the completely wrong trajectory. So there are many such examples. Priming, I think, is very well understood based on this. What else? I have a laundry list, but there's a lot of what I think is compatible evidence for this for the autoregressive model. Nothing is quite smoking gun, so to speak, I would say, but that's very, very hard to come by when you're dealing with cognitive models, right?
All right. And
Investment
while
banks.
wrapping up, we're going to go a little bit off in an extrapolating direction. Now we have what can we learn from aging and cognitive decline? And is reading then more important than real life?
Is what more important? Reading?
Reading.
Oh, interesting. Okay. Those were two different. Were those the same question? Or they seem
No,
like.
but if we're going to.
So aging, that's okay. So like I said, and I'm glad I'd already brought that up a little bit. So if you accept sort of the generative theory of memory, then the effects of aging on memory require a reformulation. What is happening? If we think about it generatively, that means that something's what the deterioration is in the sort of the influence of the past on your current generation. And I think that, and by the way, this is I didn't get to mention this, but really quickly, I remember I mentioned that the relationship between working memory and IQ. I think this is very well understood, very understandable within this framework. So I'm answering both questions, like the previous question, what kind of evidence? Well, that doesn't make any sense. Why the hell would like a storage buffer and your ability to hold things in memory, like you don't use that during, like, why would that impact so much of intelligence? And the answer is because I think it's the tip of the iceberg of this generative system. The amount of information that it's really about how much how much can you use the past to influence your current generation? It's kind of like what's your context size. It's also like how rich is your contextual representation. And so in the case of working memory, like the fact that you can retrieve and directly repeat stuff back that just happened is just because you've got very strong influence from the past. You've got really strong context. And what I think is happening in aging is a degradation of that context. And so my guess is that we're actually, if we with this framework, if we measure generative capacity, like how much, like let's say we're talking and having this conversation, stuff from a minute ago or 5 minutes ago is influencing what I'm saying. In somebody who's maybe has is memory loss to aging, it's going to influence. The 5 minutes ago is going to influence less, and 10 minutes ago is going to influence even less. And so we're going to see a much more graded kind of contribution of influence in aging. Now, that doesn't give you necessarily a mechanism for intervention per se, but it, first of all, may give you much more powerful diagnostic tools. And it also, I'm hopeful, will give us some insight into mechanism. And therefore, if we understand mechanism, computational mechanism, then maybe that'll help us understand the physiological mechanism, because I think we've been searching in completely the wrong way. I mean, I know it sounds very bold and a little, a little chutzpah, but I do think we thought about memory fundamentally the wrong way, and that means the way we thought about memory loss and degradation is probably also being thought of in the wrong way. People try to think about things like plaques and how they may interfere with neural signaling. But the question is it about the neural signal at the dendritic level, or is it at maybe the neural signal at a more macro scale when you're talking about sort of these trajectories of activation? Now, there was a second part of the question, not just about aging, and I've already forgotten it. Perfect example.
What can we learn from aging and cognitive decline, which is related?
Yes. But there was a second part.
Then the other one is it reading more important than real life? So I think we're talking about two different time series, right? Like one is the individual.
They're fairly different questions. I think
we have two different time defines here, so you should clarify.
It depends. Of course, is reading more important than real life? Well, it depends what you want to know and what you want to remember, obviously. But in terms of, so, this is something, well, I don't know if you asked that question, but that's something we were just talking about, literally like a few hours ago.
You did.
And okay, yes. And so the answer I would say is the modern use of human brains, the contemporary sort of like the way human civilization and human technology is built on language. And you're not going to get to know what you need to know in order to sort of participate at the highest levels in the sort of the culture and ecology of human civilization at the human level, right? I sometimes like to say we're not better than any other animal and anything else besides language. That's really the thing we shine at. And language-based kind of processing, right? There are other animals that can run faster, they can see better, that can hunt more effectively, that can move their bodies more effectively. But where humans live, and sort of our niche in the sort of the universe, certainly at least on Earth, is living in this knowledge space. And yes, in that case, reading is how our minds get built. Not only reading, of course, conversations like this one. I hope your mind's getting, I'm tuning your parameters just a little bit, so your generative capacity is going to now change and shift a little bit after this conversation. So it's not just reading, but it's through communication and it's through language. And reading is just this absurdly efficient way to get the best language. Especially back in the old days when publishing was really expensive. Now you could read, really pretty low grade language if you want to scroll through, through social media all day. Although I love my social media, my X channel is great. But for a lot of people, if you're getting low quality content, then maybe not as important. But even that low quality content, I would say, language itself is constantly building itself. It's reinforcing the topology. And it's making itself stronger and better. So yeah, I think that's where humans need to graze. That's where we live, and that's the food that our intellect needs to eat.
All right. Does anybody else have any other question or would like to add anything to this last one?
Yeah, this is Randall again. Okay, as far as experimental design, so like the example you gave about memorizing those sentences, I'm trying to think from an evolutionary perspective, like why would I want to memorize that? So
Oh, I
like
agree.
like
Exactly right.
like
That's exactly right.
for like there's a Chinese lady that memorizes 2,000 decimal places of pi. And some people think that's intelligence. I think it's
Yeah,
stupid.
she would have gotten eaten by a saber-tooth tiger real fast, right? I mean, so I completely agree with you that, and this is one of the stronger points I like to make, and a little bit a little rude, but I think that this entire technique of asking people to hold information and regurgitate it is totally ecologically invalid. It's like something we almost never ever have to do, and it's what actually made me very suspicious of this idea of short-term memory as this buffer. Why would you have to like repeat anything that you heard in the past? And so I'm getting rid of that entire concept. I'm saying what you heard in the last 10 seconds is you're not going to memorize it. Memorization is useless for most of the time,
Right.
but it's going to influence you, right? It's going to influence, it's changing how you're understanding what I'm saying now. It's going to change how you're going to behave and think about other stuff. And so I don't think of memorization as being in any way representative. In fact, it's this weird kind of you can force the system to kind of do memorization if you and another piece of evidence for my theory, repetition. Why does repetition lead to better memory? What is going on there? If you got a file and you stored it, it's stored. What does it mean? You don't have to, you put it in the drawer again and again, it's going to be stored better. No, it's because what you're really doing is just reinforcing a trajectory. You're reinforcing that this is a sequence that plays out once when you have in the appropriate context, you end up playing out this sequence. And so that's what I think memorization is, just this weird use, it's kind of oddball case that ended up being like the focus of a lot of cognitive psychology. Because why? Because you search for the keys where the light is. Because you can test people on it. It's you can in a 5 minute span you can get this measurement. Look, somebody can remember 7 digits. Another person can remember 9 digits. It's very convenient. It's quick and easy, but it kind of led us astray in terms of like what the brain is actually doing and what it's for.
It seems like it is true memory. It's not combining it with auditory or visual. You just have to memorize it.
Yeah, but that's not something we normally do. We don't
Yeah.
really memorize stuff unless we're forced to by a teacher or some sort of we want to show off that we can memorize stuff. Like that's very rare that we have to actually memorize a sequence verbatim.
But do you think like if somebody reads something or somebody hears something or in different contexts, would the memories be stored in different parts of the brain or in synapses? Can you transfer what you learn from one study to another study? Or they very
I think you can. I think there's a lot of transfer, and I don't think that there's parts of the brain. I think it's all one big generative network, and there isn't really a sense in which you could say pieces of information are stored in one location or another. It's that there's kind of what's changing is your capability to respond to things that may relate to that information, but it isn't really sort of encoding discrete pieces of information in specific locations.
Okay, so you're going to talk later in another month or so, and you're going to go into more depth on all this stuff.
That's the goal.
That's good. I'll be there.
Okay, I'm looking forward.
All right.
Very good. So anybody, any other questions?
And all of this is going to be recorded, and I should be able to. I sure hope it's recorded on my YouTube channel. I believe that that's how it works.
Yes, and
I just got a message that it's being transcribed, so at least there's that. That means you can feed it into GPT, which is exactly what I'll do.
Beautiful. All right, so we passed 10 minutes. Thank you so much for being with us. And I'm sure a lot of you guys have tons of questions. Don't stop yourself from sending those questions to Elan. I'm sure he's going to be super
I'd be very happy to have them.
good. Yeah, super
Check out
happy
my
to answer
Substack.
those.
Yeah, a lot of this stuff is on there. And yeah, please send me your thoughts and questions. Hey, this is a
I
great.
think it's going to help a lot to organize your second talk. around your research because you know what's coming, and then you can prepare better in order to point in
Yeah, that'd be great.
questions, right?
Yeah, I'd love to share some of my recent results next time as well.
Absolutely. All right. Well, thank you very much, everybody. And please remember that next week we are going to have Carlos Montemayor. He's going to be live from San Francisco. So please do join us, same place, same time. If you can be in person, we're going to be transmitting in the big screen at the sandbox. And if not, we are going to send you the link so you can join. The talk is going to be on attention, and he's going to focus particularly in cognitive processes and empathy. So a lot to extrapolate into LLMs later. Well, thank you so very much. And if there are any more questions, I'm going to leave.
Thanks, everybody. And sorry for running over time. I appreciate everybody sticking around.